Hello everyone. In this talk, I'm going to explain our paper, Extractors for Image of Varieties. This is joint work with Volk at Reichman University and Jalan and Zuckerman at UT Austin. I'd like to thank Bentley for helping me with the slides. So we consider the problem of constructing explicit extractors. An extractor is a device that converts low quality randomness to high quality randomness. It can be seen as a function that takes the input from a domain omega and outputs base 3. It has the property that if the input comes from a distribution that has enough randomness, then the distribution of the output would be very close to the uniform distribution in the statistical distance. Then we can ask, what do we mean by saying the distribution has enough randomness? So in the most general setting, we could consider the input distributions of sources that has enough mean entropy, say mean entropy at least k. This can be reduced to the special case where the input distribution is a uniform distribution over subsets of size at least 2 to the k. However, it's not hard to show that in this most general setting, it's actually impossible to extract even 1 bit from the input distribution from the source. This is because assume that an extractor that extract 1 bit exists, then we can look the preimage of 0 and the preimage of 1, then at least one of them has to be large. And this means that the function is not extractor. So this most general setting is too general for deterministic extraction. And there are different solutions for this problem. The first solution is to consider seeded extractors. So this means the extractor gets an additional input, which is a short independent truly random seed. It can be shown that the seeded extractor exists. The problem of constructing seeded extractors, explicit seeded extractors, is a very well-studied subject, and we know very good constructions. For example, the construction given by Goswami, Umans, and Vada. Another solution to the issue is to impose a restriction on the type of distributions that the input comes from. So we could require the input distribution to come from a small class, and then by counting argument, it's possible to show that deterministic extractors exist for any distribution comes from this small class, not explicitly, and we do not need any seed. This is what deterministic means, and we could impose restrictions of various kinds. For example, one could consider combinatorial restriction, like we could assume the source to be a two source, meaning that it has 2 powers that are independent from each other. Or it could be a k source or k independent source, or it could be a bit fixing source, and so on. And one can also consider complexity theoretic restriction, like assuming the distribution is solvable by small circuit or other computational model. Finally, we could consider algebraic restriction. For example, we could assume the distribution is a uniform distribution over a subset S that has less algebraic structure, like S could be a subspace or variety, and so on. So this last kind of restrictions, algebraic restrictions, is the focus of this talk. And the simplest kind of algebraic restriction is restriction that the input distribution, the source is a affine source. So this means it's a uniform distribution over a affine subspace. And the deterministic extractor against the affine source is what we call affine extractor. And Raz and Gabison consider the problem of constructing explicit affine extractors. And they show that if the base field has size at least n to the 10, at least polynomial, in a sufficiently large polynomial in N, then there exists very good affine extractors. There exists a affine extractor that can extract the most of the entropy. The good thing about this construction is that it outputs almost all the mean entropy, The bad thing is that it requires field size to be large enough, at least for nominal. Then, on the other hand, we could consider the problem of constructing fine extractors over a small field, like over F2, for example. And the OF2 is not hard to show that the K has to be at least the logarithmic in N for the extraction to be possible. Following the breakthrough on 2000 extractors, Lee showed that there exists explicit affine extractors OF2 that works when K is at least polylogarithmic in N. And this was later improved by Chattopadhyay, Goodman, and Liao. They show that they show the existence of deterministic affine extractors that works when K is at least omega, tilde omega log N. And finally, a recent paper of Lee further improved it, and now we only he showed that we only need K to be omega of log N, and this is optimal up to a constant factor. And it's also worth noting that fine extractors OF2 have applications in circular bonds and cryptography and so on. In particular, affine extractors and fine dispersers have been used to pass no explicit circular bonds for general circuits. Now, fine extractor, fine source is the simplest kind of algebraic sources. We can consider generalizations of fine sources. For example, De Vere, Gabson, and Richardson consider generalization called polynomial sources. So polynomial source is a source that is sampled as follows. We first pick a random point x from vector space fq to the r, and then we feed it to a low-degree polynomial map p of x from fq to the r to fq to the n. And then the output would be, the distribution of the output is what we call polynomial source. And De Vere, Gabson, and Richardson show that if the base field is large enough prime field, then there exists explicit extractors that can extract 0.99 bits from a polynomial source with mean entropy. So when the base field is a large enough prime field, it can extract most of the mean entropy. Another way to generalize the affine source is we call variety source. So variety source is a uniform distribution over set V. That is, and V is defined as a set of common zeros of low-degree polynomials. And De Vere considered this problem of constructing extractors for variety sources. He showed that over large enough prime fields Q as P, assuming that V's size of V is large enough, there exists explicit extractors for variety sources that could extract a constant fraction of mean entropy from a variety source with mean entropy K. So both of these two results require the base field to be a large enough prime field. It can actually be made more generous and work for finite field that has large enough characteristic. However, previous to our result, we do not know constructions that work in small field. Yeah. And on the other hand, we could also consider generalizations for fine sources OF2. And for example, we could consider variety sources OF2. And Golov, Neff, Kulikov, Williams, and Huber-Sirah show that if we have a good enough explicit extractors for variety sources of F2, you would give new circular bonds. And the non-trivial variety sources of F2 were constructed by Ramsgrim and also by Lee and Zuckerman. However, these constructions, while non-trivial, are not good enough to lead to a new circular bond. So in particular, for variety sources of F2, all the constructions are kind of weak, and we do not know strong enough constructions that would in particular recover the results for fine sources of F2. And now let me explain our model. So we consider the more general, even more general generalization of fine sources called polynomial image of variety. So a polynomial image of variety is a source that is sampled as follows. We have a variety V in FQ to the R, and also a polynomial map P from FQ to the R to FQ to the N. And a polynomial image of variety is sampled by first picking a random point X from the variety V uniformly at random, and then output a P of X. So the distribution of the output is what we call polynomial image of variety sources. And it's not hard to see that this class generalizes both variety sources and the polynomial sources. Because if we choose the polynomial map P to be an identity map, then we get a variety source. And if we choose a variety V to be just FQ to the R, the ambient space, then we get a polynomial source. So this class is the common generalization of both variety sources and polynomial sources. And our main result can be informally stated as follows. We obtain an explicit construction of deterministic extractors for polynomial images for varieties that can extract almost all mean entropy over large enough finite fields FQ. To state our main result more formally, let's first introduce the notion of NKD algebraic sources. We say a distribution D is an NKD algebraic source if there's a variety V and a polynomial map P specified by polynomials P1 through Pn, such that the following conditions holds. First, P equals P of U subscript V, where U subscript V is the uniform distribution over V. So this means D is the polynomial image of a variety source. And secondly, the dimension of P of V equals K, and V is an S, meaning that the number of points on V in FQ to the R is close to Q to the dimension of V. So this guarantees that there is enough mean entropy in the distribution D. Finally, V is not too complicated in the sense that the degree of V times the product of degree of Pi is almost D. In our paper, we actually use some more general, more relaxed conditions, but here, for simplicity, let's just use these conditions as part of the calculation. And I also want to mention that here V being nice is equivalent to the nature condition, which says that V is an absolutely reducible variety, which means it remains irreducible even after taking field extensions. And this follows from the long wheel bound. And this condition of being absolutely reducible also exists in the papers of De Vere, Gabson, Viderson, and also De Vere's paper. Okay, so now let me state our main result in a more formal way. So assume Q is at least the polynomial in NP and epsilon inverse. We show that there exists explicit extractors for NKD algebraic sources with 0 epsilon and output length m that is at least k log q minus a term that is of order log p plus log n d epsilon inverse, where p is the characteristic of the field. When the field is long enough, one can show that NKD algebraic source has a mean entropy k log q plus minus o log p. So this means our extractor could extract almost all mean entropy. And our result generalizes and improves the result of De Vere, Gabson, and Viderson for polynomial sources, and also the result of De Vere for variety sources. We improve both the field size and the length, and also our result only requires the field to be large enough. We do not require the characteristic of the field to be large enough. And if we choose D to be 1, then we actually recover the result of Gabson and Raz for affine sources. So the main message is that when the field size is large, Gabson and Raz show that one can extract most of the mean entropy from an affine source. And we show that this result readily extends to polynomial image of varieties. So here's the outline of construction. So our construction generalizes the construction of affine extractors, Gabson and Raz paper. So let me first explain their construction. The outline of their construction has the following steps. The first step they construct a file extractor that has a short output. And then they construct a seed extractor that is linear in the source, not in the seed. And then they compose these two objects. Namely, if they first apply the file extractor with short output to the source, and then they apply the linear seed extractor to the source, where the seed is the output of the file extractor. So note that this composition is highly dubious. It's not obvious why it works because the source and the seed are correlated. However, the paper by Gabizin, Raz, and Shetil show that sometimes this idea works. This is an idea they call recycling randomness. So here in particular, using the structure of affine structure, affine sources, and the fact that the seeded extractor is linear, we could show that this composition works. So this is construction of Gabis and Raz for affine structures, and our construction generalizes this framework as follows. As a first step, we construct a deterministic structure ext1 for nkd algebraic sources with short output. And then we construct, instead of a linear seeded extractor, we construct a linear seeded rank extractor, ext2, which is not necessarily a seeded extractor, so the output is not necessarily a uniform distribution. However, we can show that it has very high mean entropy. So we could turn this seeded rank extractor into a seeded extractor by composing with a seeded extractor that works for sources with very high entropy. Such an extractor was constructed by Goldreich and Williamson. So we compose it with our seeded rank extractor to get the seeded extractor. And finally, we compose the seeded extractor with the deterministic extractor that outputs the short seed, which is constructed in the first step. This gives a final construction. So our construction can be seen as a generalization of Gabs and Raz construction. It requires some algebraic geometry tools to achieve such construction, but at a high level, it follows the same framework of Gabs and Raz. So next, let me explain the two steps. First, let's construct a linear seeded rank structure. So we say an NK linear seeded rank function. So an NK linear seeded rank extractor is a small collection of linear maps E1 through ED, such that for every K subspace V in F cubed to the n, most of the linear maps preserve the dimension of the subspace. There is this very good explicit construction of linear seeded rank structures for subspaces. Such construction was given by Gabs and Raz, and also improved by Forbes and Spielka. However, because we are interested in extracting randomness from varieties and more generally polynomial image of varieties, we need a linear seeded rank structure for varieties, not just for subspaces, which means we want a small collection of linear maps that preserve dimension, but not just dimension of subspaces. Also, we want to preserve dimension for low degree of varieties. But we observe that actually the old construction doesn't work, because we can show that the linear seeded rank structure for subspaces is also a linear seeded rank structure for varieties. And the intuition for this is that locally at one point, one non-singular point, a variety can be approximated tangent space, which is a subspace. So because tangent space provides a very good approximation of a variety and their subspaces, their dimensions are preserved by linear seeded rank structure for subspaces. It's reasonable to believe that linear seeded rank structure for subspaces is also linear seeded rank structure for varieties. The actual proof is slightly more complicated than this intuition, but this is the reason why it's reasonable to believe it's true. Okay, so next we need to construct a deterministic extractor for the algebraic sources that has a short output. As a first step, we construct a polynomial map F from FQ to the AN to FQ, which is just a polynomial that is non-constant on any variety V of dimension at least 1, degree at the most D. So we need a non-constant polynomial. And here it's not hard to see that F cannot be linear. However, we want it to at least have low degree, because we don't want we don't want composing with F increase the degree by a lot. Such a polynomial F is called N1D deterministic rank extractor. And we could construct such a polynomial F. Here's a construction. It sends the point x1 with coordinates x1 to xn to the value sum of xi to the di, where d1 through dn are co-prime integers greater than d. And in our paper, we actually solved a more general question. So we say a polynomial map F from fq to the n to fq to the k is a nkd deterministic rank extractor if for every variety v of dimension at least k and degree at most d, the image so the dimension of f of v equals k. And we could construct the explicit deterministic nkd rank extractor. So here's a construction. Let A be a matrix such that all its maximal minors are from 0, let d1 through dn be distinct co-prime integers greater than d. We define f to be this map such that the s coordinate is given by fi that sends the point of its coordinates x1 to xn to sum of aij to j to the dj, where aij are entries of the matrix A. So this construction is actually not new. We show that it's a deterministic rank extractor in our paper, and this construction actually was originally given by Devere and Cole and Lovett to show that the variety defined by f1 through fk is a variety invasive set, meaning that it has small intersection with every variety of node. And we observed that in our paper that their proof can be adapted to prove something even stronger, which would imply our result. Okay. And we also need to turn this N1D deterministic rank extractor F into a deterministic extractor that outputs a small string. When the field is a large prime field, this was already done by Devere, Gavin, and Williamson, and the proof uses the bound-various estimates of exponential sums, and also the XOR lemma. However, when the field has small characteristic, this idea does not work. So we have to compose F with a more complicated map tau. So the issue is that when the characteristic is large enough, one can show that the distribution is pseudo-random against all the characters, so the XOR lemma applies. However, when the characteristic is small, we can only show that the distribution is pseudo-random against all except a small group of characters. So it does not necessarily work for all characters. So our idea is to design an extractor for distributions that are pseudo-random against all except a small subgroup of characters. And we construct such an extractor in our paper based on free analysis and the tool called rank matrix codes. So combining everything gives our final construction. So obviously, I'm having a lot of information. This is a very brief overview of our construction. In particular, there's some algebraic geometric tools that I did not talk about. But the main message is that over large enough finite field, one can extract almost all entropy from the algebraic source. When the source is an affine source, Devere and Raz and Gabs already show that one can extract most of the main entropy. And we show that this result readily extends to more general family of polynomial image varieties. So here I'll only give you one open problem. So can we reduce the field size? We already obtained the extractor that could extract most of the main entropy. However, our field size is large, so it will be very interesting to reduce the field size. In particular, our result holds when Q is at least polynomial in ND and epsilon inverse. Can we get rid of the dependence of the field size on the character N? That'll be very interesting. So if you have questions, feel free to send me an email. Thank you for your attention.